Ooh. All right. God, my live preview is not live. I swear. I always look over to the stream preview on YouTube Studio, and it just told me the timer had 3 minutes, which is obviously not true. All right. So, much like the last couple days, we just have a list of integrals to do today. And the integrals for today, they're going to use a variety of techniques that we've talked about so far. And just see if we can figure out what to do. So let's start off with number 1 here. So these integrals, they're going to be a little bit trickier than the ones we've done over the past couple days. But it's just sort of like seeing, how these techniques we have can be applied. All right, so let's start off with this one here. So I don't like the dx on top personally, so I'm going to rewrite it this way. I like, to me, this looks better. Okay. So if we look at something like this, we have a little bit of a problem, right? There's, we'd like to try and get this to work out. So, let's see what we can do here. So looking at this integral, there's nothing really nice patterns. There's no u substitution that's obvious for us here. So sometimes we just have to try and manipulate the expression into a way that maybe makes a little more sense. Sometimes you might manipulate the integrand as it is. Sometimes you might try and do a u substitution and see if that clears anything up. So there's a couple approaches to this one. And it's really up to you what you want to try and do. So here, what to me makes the most is that I have 2 exponential terms. So what I want to do is try and at least turn the exponential parts into polynomial. Right, this is what makes sense for me. Right, so what I'm going to do is I'm going to say u equals e to the x. Okay? And I'm going to do this because, well, that'll allow me to change this e to the x here, but it's also going to allow me to change this e to the minus x, right? That's going to turn into a u to the negative 1 power. So then if I pick du, that's going to be e to the x dx, which, might cause a little bit of an issue here, but let's see what we can do. So when I plug all this stuff in, here I get 1 over u plus u to the negative 1. Now again, the dx, if I move this over, this is 1 over e to the x du equals dx. I just divide this e to the x over. All right, but that's not entirely useful, right? Because now this mixes x's and u's. But much like when we were doing some of those u substitution things, we can use this here to say that, no, this is 1 over u du, right? So now everything's in terms of u. 1 over u du. All right, and now let's multiply this out and see what happens. 1 over, multiply the bottom out, we have u squared plus 1 du. Is that an integral we know how to do? So hopefully this one looks familiar. It's one of my favorite integrals. This is arctangent u plus c. Okay. And now that we have that, we can just pop u back in. Arctan e to the x plus c. That's it. So this integral looks tricky, but really the trickiness of this integral is that it's not really written in a form that we can work with. We have to edit or manipulate the functions. Another thing we could do for this integral, we won't completely work out the answer this way, but another way we could work out this integral is say, well, I don't like negative powers. Right, so let's try and work with that. So I'm going to take this, and then I'm going to multiply by e to the x over e to the x. Right? Then what that's going to do is give me an e to the x on top. E to the x times e to the x is e to the 2x. And here the e to the negative x and the e to the x cancel each other out. We changed colors somehow. 1. And now if you try that exact same u substitution, it's going to work out a lot quicker. Okay, so you still want to do u as e to the x here, and then you're going to wind up right immediately this spot right here. So you notice we kind of did this sort of did the same trick in both of them. We somehow had to essentially get rid of that negative power on the bottom. And just, in the first step, it was like, well, we'll use the substitution ends up getting rid of it. Whereas in the second one, we explicitly do it ourselves first. And then, then do the integral. But either way, we end up here. All right. So any question about that one at all? All right. Awesome. So hopefully that wasn't too bad. Let's go ahead and try another one here. 2. All right, so problem 2 here. Cosine of x plus sine cubed of x over secant of it. Right, yep, dx. All right, so how do we do that one? So if we try here to make u the denominator of this one, we're going to have a little bit of a problem because the derivative would be secant times tangent, and none of that is hanging around up here. So we have to see what we can do. Another option that we always have is to just, again, rewrite this function, right? If we rewrite everything in terms of sine and cosine, we can usually get a good idea, a good handle on what's going on. So let's do that, right? So here we have cosine x plus sine cubed of x over 1 over cosine x. Okay, now let's simplify that expression a bit. So since we're dividing by 1 over cosine, that's the same as multiplying the top by cosine. So we essentially have cosine squared x plus sine cubed x cosine x dx. And now that we have this, now that we have this, what can we do? How can we evaluate this one? So this one here really has to be done in 2 parts. So to do this in two parts, we need to do the cosine squared part, and the rest of this separately. These two have to be done separately. To do this first part, we're going to use a trig identity. Cosine squared x is 1 plus cosine of 2x, 2. All right, we need to use that here. On this side, we're going to have to do a u substitution. Can you think of what substitution you might use here? Sorry, what substitution you might use here? So that substitution there, substitution has to be u equals sine of x, because then dx, du is cosine x, x. And when you have that, right, so now this first integral turns into integral 1, let's be a little cheeky with it. This over 2, I'm going to factor that out as a 1/2. Be 1 plus cosine 2x, x. This integral over here is simply going to be integral of u cubed, u. So, integrate this. We have 1/2. This is going to be x plus 1/2 sine 2x. For that first part. For this part, we get 1/4 u to the 4th. And all of this plus c. And now we just swap u back for sine of x. And we have 1/2 of x plus, maybe it'll look nicer to just distribute that 1/2. 1/2 x plus 1/4 sine 2x plus 1/4 sine to the 4th x plus c. And there we go. Right, so we get a bit of a interesting integral here. Right? Not too bad. Any question? All right, cool. Okay, yeah, we're still. All right, so let's go ahead and do problem 3. Problem 3 here. So this one has a typo. Give me 1 second. I made a typo in my problem set for the first class today too. I think that's probably +7 at the end, not minus. Yeah, let me double check. Where did the heck did this problem go? those in another second. I really want to do a problem like this one. Quite an interesting technique we have to do. Was that right? Oh, okay. Never mind. I didn't make a typo. Alright, I saw all the negatives down there and I was like, this just has to be wrong. Oh, we're good. Okay. So when we look at this integral here, right, I guess this just has to work out then. Alright, let's see. So if we look at this, don't be fooled like I was by that negative sign down there. It's gonna be okay. Looking at this stuff on the bottom, we have there's a little bit of a problem, right? We don't have any way to deal with this. But what we want to keep in mind is we do have a couple, or something that looks maybe close-ish to this. We do know that let me do this in blue, the integral of 1 over square root 1 minus u squared du is arcsine of u, plus c, of course. So if we can somehow get that kind of form down here, we might be okay. So to do that, we do something called completing the square. So hopefully you remember this from back in algebra. So minus x squared minus 8x minus 7. How do we actually integrate that? Or sorry, how do we complete the square on this? So let's first off pull out this whole negative business. Right? And what I'm going to do is actually group these two together, and then I'm going to leave a space. Then I'm going to leave this 7 on the outside. And what I want to do is I want to add a number inside of here so that I can factor this as x plus something squared. The way you get that number is you take this 8 and you divide it by 2. Right? So that's saying we should add, divide it by 2 and then square it. So divide it by 2 is 4, square that is 16. Okay. So since we added 16 in here, we also have to subtract 16. Right? We can't just add something without... We're essentially adding 0 here, right? We can't change the expression that we have. Okay. So what that means is we're going to factor out this negative 16. We're going to pull that out of the parentheses. So here we have minus x squared plus 8x plus 16. And then negative times negative 16 is plus 16. So this is negative x, right? X plus 4 squared plus 9. All right? So this is completing the square. So that integral we have is equal to, I'm going to write this as 9 minus x plus 4 squared dx. Now we're getting somewhere. This is something that looks really close to the arcsine integral. The only problem is this 9 right here. But that 9 turns out to not really be such a big deal because we just factor it out. So if we factor the 9 out of the bottom, well, let's do this really carefully, just so it makes sense what's going on. So I want to factor 9 out of that stuff there. So it factors out as 1 from the first part, and in the second part here, this. So that makes sense. All right, now I want to manipulate this a bit. I'm going to pull the 9 out of the square root, so we just get this 1/3 out here. integral 1 over square root of 1. Now here, I'm going to combine this into one squared term. I can write this as x plus 4 over 3 square. X plus 4 over 3 quantity squared. Okay. Now at this point, can you see what we need to do? All right. So how do we do this? Well, we're gonna set u to be this stuff inside the square. This is why I grouped it. So then du is gonna be 1/3 dx. Okay. So let's go ahead and get that substitution in there. Let me point out here that the 1/3 dx is right here. So I can just pull all that out. And we actually do have just integral 1 over square root of 1 minus u squared. It's quite nice. All right. Oops, that's du, sorry. All right, so this is arcsine of u plus c. And so plugging our substitution back in, x plus 4. Okay. So there's lots of really interesting integrals you can get here. Any questions? Excellent. Well, hopefully we're hanging in there with these integrals. All right, this next one's a bit deceptive. X e to the square root x. So this one's over here looking like, looking like an integration by parts integral. But let's see what happens if we try integration by parts. Right, because think, if we had x squared e to the x, which is what hopefully this maybe looks like, we could do that with integration by parts. Just do 2 integration by parts in a row. Okay, but that's going to turn out to not work in this case. So we'd want, So you might think this would be the good choice here. Sorry. We don't want to do that. We could try this. Does that work? Even that gives some problems, actually. So, more of the story here is it seems like we want to do integration by parts, but there's actually nothing that's really going to work here. I know there is a choice you could use here, but it's just going to make the integral. But the point here is that integration by parts is not the answer for this problem. Turns out we actually want to do a substitution here first. The substitution is the square root of x. That square root of x up there is really terrible. So let's get rid of it. Right? It's probably not going to give us an integral we can immediately do without any other technique, but it's going to get rid of that square root, which is causing a problem. So du is going to be 1/2 1 over square root of x dx. So when we plug that in here, what's going to happen? Well, we have an x here and we have a dx. So, you know, this x here we can get at. Since x is square root of x squared, this x turns into a u squared. Okay. We have e to the u. Now, what happens with the dx here? Well, here we have 2 square root of x du equals dx. This is just u. So we have 2u u. What this is going to turn into. Box that stuff off. Right, so we have to be a bit clever with the u substitutions. So what we run into now is 2u cubed e to the u du. Okay. So now this is actually an integral we can attack. Okay. So to do this, we just have to keep applying integration by parts. So here, then we have u is, may as well make it 2u cubed. Oh, we should use a different letter. Let's use v and w. So I'll use w for u and dv, v in the normal way here. All right, so dv is going to be e to the u. So then dw is 6u squared u. v is e to the u. So we have 2u cubed e to the u. Minus, in this case it'd be v dw, so minus 6u squared e to u. All right, and then we have to do it again. So w is 6 squared, v u du. W is 12u u. V is e to the u. So we get 2u cubed e to the u minus parentheses. Very important here to have that parenthesis. In this case, w times v, 6u squared u minus v du minus 12u u. And then I bet you're going to be really surprised at what comes next. We get to do it one more time. So w, 12u. That makes dw equal to 12d. So dv is going to be, again, e to the u du. So v is u. All right, so we do this one last time. And we get 2u cubed e to the u minus 6u minus parentheses 6u squared e to the u minus, and then another parentheses, what do we, 12u e to the u minus the integral of v dw 12e to the u du. All right, so let's start sorting out all this parentheses stuff. 2u cubed e to the u minus, we'll distribute this one first. This one, we get minus 12u e to the u plus 12e to the u plus c. All right, so now we'll distribute that last negative, and we need to replace all the u's with what they were before, which is square root of x. So at the end of the day, our answer is going to be 2u to the 3 halves e to the, square root of x minus 6x e to the square root x plus 12 square root of x e to the square root of x minus 12 e to the square root of x plus c. So it's quite impressive, I think, that such a simple looking integral can produce this thing, right? So any question about this one at all? Yeah, again, just several steps of integration by parts, and setting yourself up for that with a substitution. Which reminds me, I need to put homework for integration by parts to do. So I'll do that one in this one. Sure, we're all caught up on that. Okay. Oh, come on. So now that we got that, let's look at the next integral. 5. This is 0 to 2 x cubed e to the x squared dx. So let you think about this one for a second, see if you have any thoughts on it. Then I'll have a go at it. So what we want to do here is a u substitution. That x squared up here is causing problems, so we're going to substitute that out. Then du is going to be 2x dx. So let's look at what we have here. So this integral, before we do the substitution, let's try and break it into parts that we're going to use. So here, we have e to the x squared. That's going to be substituted out. If I take one of these x's away and put it with the dx, I can get 1/2 du there. So here we sort of have, here's e to the u, here's 1/2 du. But what do we do with this x squared that's left over? You think about that. We have an x squared right here. This is just a u. So, oops. So, no big deal. So this is, well, this right here is what it's going to turn into. 1/2 u e to the u du. All right, so now we have to change our bounds. So we plug the 0 into the x squared. 0. We plug the 2 into the x squared and we get 4. All right, so u of 2 squared is 4. U of 0 squared is 0. All right, so just pop those in here. There's our u, our new bounds. And then how do we integrate this? Oh, ue to the u is sort of like everybody's first integration by parts example, right? So I'm going to use w and dv again. So if we do w is, let's just make it 1/2 u. dv is going to be e to the u du. dw is 1/2 du. And v is just e to the u, of course. Okay. So w times v minus the integral of v du, or v dw in this. So that's going to be 1/2 ue to the u minus 1/2 u after we integrate it and go 4. How's that look? Now we just have to plug this in. So plug in the 4, we're going to get 2e to the 4th minus 1/2 e to the 4th. Minus, plug in the 0, we're going to get 0 minus 1/2. And so simplifying this, we're going to have 3/2 e to the 4th plus 1/2. That. Right, so this one is, compared to the last one, this one was relatively straightforward. So any questions at all here? All right. So let's go ahead and jump to the next one. So this is sine 2x times ln ln of sine of x dx. So what do you think here? Is going to go on with this one. I'm like way off camera, but wanted to relax on my arm for a second. All right, so what kind of substitution or trick manipulation could we do for this one? Or what makes this problem hard? I shouldn't say hard, but non-obvious. So this problem here, what we want to do is make the substitution u equals sine of x, because that sine inside of the ln is noxious. But if we do that, we need a cosine x somewhere to handle the du. We don't have that. At least not explicitly. There is a way we do have that. There is a trig identity. Sine of 2x equals 2 sine of x cosine of x. With this trig identity, we can make a cosine. So this integral turns into 2 sine of x cosine of x times ln of sine of x. So if we look at it this way, can we do this now? We should be able to, right? U is sine of x, which is what we wanted. Du is cosine of x dx. So this whole part is right here now. And the u, we have one here, and we have another u out here. Right, so this is integral of 2u ln of u. What do we do from here? Well, we just have to do integration by parts. So w is 2u dv ln of v. I did that backwards. Remember, the log one is the one that we choose to differentiate. The ln of u. This should be 2ud. So dw, 1 over u du. v is u squared. w times v, u squared ln of u, minus the integral of v du, which is going to be u du. Or v dw, I should. So, it was u squared ln of u minus 1/2 u squared. See? Right? And then, now replace all the u's with sine. We have sine squared of x, ln sine of x, minus 1/2 sine squared of x plus c. Here we go. That's it. So, again here, we just want to look for ways to sort of like use a u substitution to turn an integral into something manageable. And, you want to look at, like, if I do want to try u substitution, will it work? If I want to go to integration by parts, will it work? Let's see. 5 minutes left. Actually, the next one's pretty quick. Let's look at this one here. 0 to pi over 9 sine of 3x over cosine of 3x plus 1 dx. So think about this one for a second. Might want to do. Right. So in this one, the problem is the cosine 3x on the bottom, really. So we can take this entire bottom, because that plus 1, when we do du, it's going to go away. So if we make u equal to cosine of 3x plus 1, then du is going to be negative 3 sine 3x. So when we substitute that stuff in, we get 1 over u, negative 1/3 du. Okay, hopefully that seems good. But now, we need to deal with the bounds. So we just plug these in. So plug 0 in, u of 0, cosine of 0, plus 1, 2. U of pi over 9 is cosine of pi over 3 plus 1, which is 3/2. Okay. All right. So let's integrate that. Negative 1/3. Integral of 1 over u is ln, absolute value of u. And we're evaluating this from 2 to 3/2. So this is negative 1/3 ln of 3/2 minus ln 2. Right? So, this is good enough. You can simplify this a little bit, but it's not really worth it. Not really worth it. Right? So, any questions here? All right. So, let's see. Yeah, these last two actually aren't too bad. Let's go ahead and try and knock these out. this one here, this one looks a lot like, it has the square root of 1 minus something on the bottom. So if we look at this in the right way, if we put this as x to the 10th squared, this should remind you a little bit of arcsine. So if we say u is x to the 10th, that's what's really causing the problem down here. Du is going to be 10x to the 9th. Then this integral becomes 1 over 10 integral 1 over square root 1 minus u squared du. Right? And so we get 1 over 10 arcsine of u plus c, which is 1 over 10 arcsine x to the 10th plus c. That's it. Okay. A pretty straightforward integral, I think. At least compared to some of the other ones we've, right? So I really want to do this last integral here. Go ahead and move on to that. Just let me know if you have any questions. So this last integral here, secant cubed, this one's a bit of an interesting. We don't have anything to deal with secant cubed directly, but we know how to integrate secant squared. So what we often do with integration by parts is we take what we have here, we pull out the sort of the most complicated thing we can integrate, and from there we just have to differentiate the rest. But differentiation is rather easy compared to integration. So if we look at secant cubed, so I have secant x, secant squared x dx. Right? So I write it in this way because I know how to integrate that. So I'm going to make this dv. This, well, I'm stuck with, so that's going to be my u for the integration by parts. Right? So then du is going to be secant of x, tangent of x. And v is just going to be tangent of it. Right? If this is my u and this is v. So we have u times v minus the integral of v du. Let's see. V du is tangent squared x secant x dx. Now, have we really made things much better? Turns out the answer is yeah, we actually have made things quite a bit better for ourselves. So this tangent squared here, we can deal with. We have a way to deal with this. Right? So you might remember this identity. Oops, not plus 1, equals 1. If I take this identity and I divide it by cosine, I get tangent squared of x plus 1 equals secant squared of x, which means that this integral turns into secant squared x minus 1 secant of x d. And so if I expand all of this out, I get secant of x, tangent of x, minus integral of secant cubed of x. So I'm going to split this integral into two pieces, plus integral of secant of x dx. Okay. Now you might remember when we did that integral of e to the x dx, look what happens here. Hopefully that rings a bell, because this tells me that 2 integral secant cubed of x dx, if I just move this to the other side, This is secant of x, tangent of x, plus integral secant of x dx. And I can integrate secant. So let's go ahead and just finish this off here. Integral secant cubed x dx is going to be 1/2 of secant of x, tangent of x. If you remember, the integral of secant was that one that was a bit interesting, a bit odd, was ln of secant of x plus tangent of x, and then plus c. Kind of an interesting little trick to this integral. So any questions about that? All right then. Well, seems like that'll be it for today. So if anyone has any questions, have a good afternoon. I'll see you on Friday for some new and exciting integration techniques.